we have already completed writing sin I and sin R values. To quickly recollect, we got I and R. Using I and R, we observed our sheet, this particular sheet, to get sin I and sin R values. I also calculated sin I by sin R. Look at all these numbers. All of them are very close to 1.5. If you take an average, there's a good chance all these numbers will end up around 1.5. So we are getting a little bit of variation. They're not exactly 1.5 because we are not robots. If I was a robot and if I would have performed the experiment with the semicircle slab and laser light, each and every time I would have got 1.5. These tiny variations we can consider human errors, the errors that I made. Because of that, we are seeing some changes from 1.5. So ideally, every reading is 1.5. Now, let's think about observations. Our first observation is, other than 0, look at all the other numbers. Which is a greater number? Is angle I greater than angle R? Or is angle R greater than angle I? So as you observe carefully, angle I is greater than angle R. This also means that light is bending towards the normal. Try to recollect, this is our interface. When light hits the interface, we draw a normal, and this is a bigger angle. As soon as it goes to the other side, this side is rarer, this side is denser, lighter and heavier. It bends towards the normal. So angle R is smaller and angle I is greater. See this 20-13, 30-20. I is always greater than angle R when light travels from rarer to denser. That is our first observation and related conclusion. Now look at the next observation. As incident angle changes, the sin I by sin R does not change. Don't worry about these specific numbers. I already told you, if I was a robot, I would have got 1.5 each time. So sin I by sin R is a constant number. It does not depend on the changes in incident angle. But what does it depend on? It depends on the materials. For this experiment, we used this glass slab and we used laser light. We had air and glass as the two materials. If I change any material, that means if I change this glass and use soda glass or some other glass, then the result would be a little bit different. So whenever you change the materials, this sin I by sin R will change. And another factor it depends on is the wavelength of the incident light. This laser light is green in color, right? So if I have used red laser, then I would see a little bit of difference. So by the way, this sin I by sin R is called refractive index. The next 30 seconds to 1 minute, I will talk about that refractive index. But for now, understand the factors it depends on. It does not depend on the changes in incident angle, but it depends on the materials used for this analysis. And second one it depends on is the wavelength of the incident light. Now let's talk a little bit about refractive index and we'll move on to the next topic. So in our experiment, we got the refractive index as 1.5. Try to remember which materials we used. We used glass and air system. If I would have used water and air, that means the denser material is water and rarer material is air, then I would have got a refractive index of about 1.3. For water and air system, the refractive index is 1.3. If I would have used diamond and air, the refractive index would be far more greater than 2. It will be way more higher. So try to observe these numbers and understand that when the denser material is changed, the refractive index changes. Also, as the density of the material changes, the denser medium, if it becomes more and more denser, the refractive index will increase. Diamond is denser than glass, so its refractive index is more. Glass is denser than water, so its refractive index is more. So as optical density of the denser material increases, the refractive index also increases. But what about bending? Now look at this particular surface. This is our interface, as we have already been seeing. I told you, right, this is our incident ray, this is the normal. If it's the same material on both sides, imagine this is air and this is also air, then bending would never happen and light would have traveled straight without bending in a straight path. But since we are using a denser material than air, this is the rarer material, this could be our water, glass or diamond, instead of going in the straight path, it is bending a little bit. Okay, so as refractive index increases, the bending also increases. For example, if this was water, the bending from the original path would be very little, just like this. So imagine this is water, H2O for water. Now if I would have used glass, instead of going straight, it would bend closer, but it would bend a little more than the water scenario. So this one is glass, and last one for diamond, as the density is more, the bending would be more. So it would bend furthermore, much more closer to the normal. This would be the scenario for diamond. So I hope you got a sense of what refractive index means. It tells us how much bending would happen from the original path. This is zero bending, with water less bending, with glass a little more bending, and with diamond enormous amount of bending. Okay, that is what refractive index is, and that is what we learned from this amazing topic. Thank you.